And hello, welcome back everyone to our OpenFoam discussion. In the last video, I was talking about some updates for you and how I've actually switched to Linux Mint, and of course I did some repository cleanup. Alright, so in this video I want to talk about adding some turbulence to this hot sphere in our case, which is actually pretty simple, but you got to have some background. So what you should do is to go to the description below. For example, here's the video. Go to the description below. Please go and see quickly my turbulence modeling playlist. The GitHub repository is there, and of course you should see my OpenFoam intermediate playlist as well. You will need those prerequisite knowledge and some of the geometry I might use in future, because there I'll tell you about the background, the theoretical background behind turbulence, and also the theoretical background behind turbulence, and also what else? How to mess around with the Git, how to do meshing and everything. Okay, but anyway, without further ado, I'll try to edit this file. So I've actually made a fine mesh sphere oil LES, large eddy simulation. I use Snappy Hex Mesh to mesh it, but in future I might use something like Salome and FreeCAD to do my meshing, especially for more complicated shapes. But for now, I'll just talk about adding turbulence models, which is in all pretty simple. Okay, so as with any case I actually want to do turbulence models, I'll actually go to the foam tutorials just for reference, and I will go to buoyant pimple foam or CHT multi-region foam, for example. CD CHT multi-region foam, and I will grep-r, which is to find turbulence models. Okay, so here doesn't seem to have it. Or maybe I'll just write turbulence. Yes, it'll be turbulence properties. It'll be in turbulence properties. So that's where you will have all these models. So I can go to reverse burner, for example. Reverse burner that will have the turbulence, and since this is a multi-region, you will see all of this all of these in different files. So I'll go to the gas region and see what the turbulence properties are here. So over here you'll see that this is a K epsilon turbulence model. Alright, but for now I actually want to get into LES modeling. Okay, so I'll do LES modeling, and I'll do K omega SST IDDES. If you don't know what that is, just search CHT multi-region foam, and I'll type list turbulence models, and you'll see all the turbulence models available here. Okay, the ones I'm mainly dealing with are the K omega SST and K omega SST IDDES. One from the RAS side, one from the LES side, just as a demonstration. Plus these are pretty popular models anyhow, so I will try to use these models. Alright, I'll try to use these models. So let's try and start. I'm going to try the K omega SST IDDES, but there's no K omega SST IDDES in the OpenFoam tutorial suite. Okay, but let's start slowly. All right, so I'm going to go to constant, and first thing to do is to go to oil. All right, go to oil and go to turbulence properties, VI turbulence properties. Okay, now it's just laminar, and to add turbulence I don't want to put it in laminar. I'll use LES, and there are a few things I need to change. Alright, let's go to incompressible, because that's where the IDDES model is found, the tutorial case. So let's grep-r IDDES, and you will find it inside this surface mounted cube. So I can go to open this file. So I'm going to copy. So I go in VI, pimple foam, LAS, surface mounted cube, full case constant turbulence properties over here. And this is what you will find here. So I'm just going to copy this whole entry here and I'm going to paste. Alright. So let's explain what this is. LES stands for Large Eddy Simulation. If you specify the simulation type as LES, you must put all the relevant entries here. So turbulence will be on. LES model is Spala Omerus, but I'm going to change it to K omega SST. Okay, K omega SST IDDES. So if you forget how to type this, very simple. CHT multi-region foam list turbulence models will help you. Okay, so it will show you K omega SST IDDES. So type it exactly as you see it here. K omega SST IDDES, small letter K, big letter O, and SST together. No dash, no dots, no nothing. So VI turbulence properties. So I spelt it as such, K omega SST IDDES. The rest I'm not going to touch. One very important thing to remember is this parental number. So parental number, I'm just going to set it at 0.9 PRT. This is the turbulent parental number, very important. Okay, I'm going to set it at 0.9. Alright, so when you do this, it will set a uniform turbulent parental number all in your fluid, because the way they handle turbulence is basically they will use your turbulent viscosity nu T. Okay, they will use this turbulent viscosity nu T, which is not added here yet. Alright, then they will just divide it. I think divide or multiply, I can't remember which is which. Yeah, but they'll multiply it by some factor of this turbulent parental number. If you want more details, again, go and look at my turbulence modeling series. I explain it in depth there. In this video, I'm just showing you how to do the syntax right. Okay, so I'm going to CD here, and okay, let's go to 0 to see what we need. Okay, so we have nu T. Alright, nu T is the main thing you'll need there. That's the turbulence itself. K is the turbulent kinetic energy. Alright, but we also need an omega field. So there are a number of fields to add. Why am I adding all of them? Okay, nu T stands for turbulence viscosity. So that will actually store, because usually in turbulence we model our turbulence as an artificial increase in viscosity, and the velocity fields we actually resolve are the average velocities, not the instantaneous velocities. So to calculate nu T, we will need K, which is the turbulent kinetic energy. We also need omega, which is the turbulent frequency. That's why we are using that. And of course, the heat transfer portion, we will need alpha T. That again is calculated through our turbulent parental number. Okay. So again, if you forget what to add, you can actually try running the thing first. So I'm going to do an all run serial pre. Alright, so this is actually going to just do my meshing portion for me. I'm not going to run this CHT multi-region foam yet. Okay, so this is going to start running my meshing. Later, I can do a CHT multi-region foam just to test if, hey, is this thing going to work correctly? Is it going to need extra files? Is it going to need FV solutions and everything? We can use this to check. Okay, so the meshing has been done. I can do a check mesh here. Alright, this will check how many cells there are and everything, and the quality of the mesh. And it looks like here I have about 200,000 cells. It's not very small but not very big. Okay, so that's how again, I'll show you check mesh. if you want to count the number of cells, you go here, you take a look at how many cells there are here. This is how you count the number of cells, 176,000. Okay, so this is how you count the number of cells there. Alright, so let's run CHT multi-region foam, and again there will be some error here because you will need a few things. You need not just the fields here, you will need to add in entries into your FE schemes and FE solutions. So let's go through it one at a time first. Let's go to 0 original, and I'm going to copy over the epsilon field into omega. Okay, I want an omega field. Okay, so this is not omega. So let's go and see what the omega field entry should look like in terms of units. Okay, grep-r k omega SST, because I'm gonna search first for the k omega SST case, because the way k omega SST case and the k omega SST IDDES case, the way these files are structured are remarkably similar, so I can copy some of them over, some of the features over. So let's go to this case, pimple foam wing motion blah 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 2D. Okay, so this is a dynamic pimple foam, but again, okay, maybe I don't want a dynamic pimple foam. Let's go to CD foam tutorials and grep-r k omega SST. So I'm searching for this case, and I'm searching for k omega SST case because again the case structure is very similar. So I'm just going to copy over some of these entries. So that's why the tutorial file is very good for you to have this kind of reference. Okay, so you'll find it in multi-phase, you'll find it in compressible, and one of them is in heat transfer. So you'll see this windshield defrost. This is where I want to take a look. Okay, because here is where you have your k omega SST. Alright, so this is what it looks like. Alright, so I want to take a look at the 0 file or 0 original file. I'll look at the exterior, maybe that's where you'll find the cases. That's where you'll find the relevant files. You see there's alpha t, there's k, there's nu t, there's omega, p and prgh, t and u. Okay, so I want to take a look at the omega. Okay, so this is what the omega looks like. This is what values there are. Dimensions should be as follows here. This is actually -1 in terms of times. This is per second. So I need to change the dimensions file to this. Okay, internal field, I'll leave it uniform 0.01. All the rest I will not do anything. Okay, but I will need to edit the change dictionary there because it's adding in something. Okay. Right, so over here you will have some wall functions over here, which I won't elaborate just yet. But I need to add in the other entries in the 0 original file. Then I'll just so-called call it a day. I'll need to run the remeshing again. Okay, let me slow down. I think I'm going too fast. Okay, basically I'm going over file by file. Okay, the overall view is that I'm going through file by file. First the 0 original file, then the constant, the stuff in the constant file, then the stuff in the system file. Alright, so after I change the 0 original file, I will need to do some remeshing because there is this thing called split mesh regions, which will copy stuff from the 0 original file into the 0 file here. So because I'm doing that, I'll need to change all of this. I'll need to remesh basically. Okay, so there will be there will be an omega field inside the oil field here. Okay, CD oil. Okay, so that there'll be omega over here. Now there is no omega inside the 0 directory, but inside the 0 original directory there is an omega field. Okay, so omega field is here. Okay, omega field is here. I will need a new T field as well. So I'm going to copy this over, the new T field. So CPAR alpha T, new T. Okay, fortunately the units are pretty much the same. Okay, so alright, all of these entries over here are the same for CHD multi-region form because we are going to use change dictionary to sort of change everything first. We're going to use change dictionary to define our boundary conditions, not change the files here. I just need no blank files in here because that's how the code works. Because it will take the blank files, the blank templates from this 0 original file, then it will use change dictionary to change the entries in there. So there's alpha T, epsilon, nu T, omega, K. Anything else we are missing? Okay, there's T, U, P, R, P, R, G, H, omega, nu T, K, and alpha T. So I think all the files are basically here. I just want to double check what units nu T will be in. We are nu T. Okay, so nu T should be in these units, and so should alpha T. Okay, let's paste. Okay, so once this is done, I'll just delete. I'll just close via alpha T. Alright, the dimensions should also change to meter square per second. So this is in for the length scale, and this is for the time scale. So it's meter square per second. If you're not sure, you can always look here via alpha T. Okay, it looks like this thing is actually in it is in this kind of units, so that's a little strange for me. Okay, but never mind. I think I'll just follow the OpenFoam convention because I think there are actually some the units are not exactly the same as, you know, this thermal diffusivity. This is alpha T, which is of course supposed to have the same units as alpha, which is thermal diffusivity, which is meter square per second. But I think the way they structured their code, they actually changed the way the units are defined. Just like you know, in a pimple form, pressure is not it's not the full, you know, it's not the full pressure, so to speak. It's not a dynamic pressure where you have mass included. You have some sort of kinematic pressure, which is actually P over rho. So I guess something to that effect may be also present here. It may also be present here. So that's, I guess, is why alpha T is structured as such. But anyhow, for this file, we are pretty much done. It's the 0 original file. So I can just do a all clean, and I'll do a all run serial pre. Okay, so that should actually help us to get the correct files out. Then after that, I'll need to see if I need to change anything else in the constant file. But as far as I know, the constant file is the only thing you have to change here is the turbulence properties entry, which is over here. Okay, then the next things we mostly need to change will be in the system directory. Okay, let's see, exterior. Yeah, the only thing you need to change with respect to turbulence is this file here. Anyway, I'm just going to copy and paste this here just for reference, and I want to move on to the RAN. When I want to move on to the RAN simulation, the Reynolds average Navier-Stokes simulation, it'll be much easier as well. So 0.9, oops. Okay, so yeah, anyway, I'm going to leave all of these here so that when the time comes, yeah, time is up for me, I don't want to take too long. When the time comes, it'll be easy for me to switch over from LES to RAS, because all the entries are here, but I'm just going to specify the parental number here. You can do that. As for dynamic parental number, I don't think that, as of now, OpenFoam doesn't really have the capability to do that. Like similar to how we have a dynamic LES model, but in terms of capability for dynamic parental numbers, you have to kind of code it in yourself. It's not natively available yet in this version of OpenFoam anyway. So let's take a look at the 0 file, and let's take a look at oil. We'll see that our alpha T, K, epsilon, everything is here. Okay, if we look at epsilon, okay, we will have our epsilon wall function because we already ran our change dictionary on this. But if you take a look at alpha T, okay, we don't have anything here. We don't have anything here actually. It's all kind of blank. We'll need to because yeah, all of this is kind of blank because we didn't change anything in the change dictionary file. So there's still work to be done. Most of them will be done in the system directory. We'll need to change the change dictionary file, FV solution, and FV schemes for the fluid portion. Alright, then we'll run our CHT multi-region form to see whether we've changed everything right, and then we'll kind of maybe check our results from there. Okay, thanks for watching. I'll see you guys again. Bye bye.